Hello, I'm Dr. James Dborin, co-founder and head of research at DoubleWord AI, and in today's Behind the Stack video, we're going to be talking about which inference engine you should be using. So, inference engines are obviously a crucial component of self-hosting language models. It's the bit of code that actually gets used to run the model in a loop and perform all the computations and get you your tokens. But there are a lot of inference engines available, a lot of open source ones that you can choose from. And the question is, what are the various trade-offs in choosing them, and how should I go about choosing it? So we're going to discuss that today. And broadly, this decision maybe falls into two camps. I would say in camp one, you have what I'm going to call local deployments. And in camp two, I'm going to call something like a multi-tenant deployment. So what do I mean by these? So a local deployment, I kind of mean you're deploying on your laptop, on your desktop, on your phone, on your iPad, something like that. Something where you're the primary user, the only user of this model, and also it could be deployed on sort of a wide variety of hardware. There's obviously a lot of different hardware that powers modern laptops and phones and things like that. And so by this, I sort of mean you want to run on your laptop, some sort of Mac Studio, MacBook, phone, some sort of desktop, maybe it's a gaming PC that has a GPU or similar, but you're interested in just individual use of these sorts of things. And then multi-tenant is the scenario where you want to deploy a language model and then give many people access to it. It might not necessarily be many different people, but it might be sort of high concurrent access of the model. So this would be the case if you're providing an API. Maybe you're a company hosting an internal language model. Maybe you're OpenAI and you're giving the world access to its GPT models. Maybe you're giving access to Llama 4 internally in a company. Maybe you're running batched workloads. Something like that, where you have many users of a single model. And these two things come with very different considerations that you're going to need to take into account when deciding inference engines. So in local deployments, the kind of considerations you really care about is maybe portability. If you're designing an inference engine for a local deployment, it better run on hundreds of different pieces of hardware. Who knows what your users are going to come to you with? Maybe you want to optimize for binary size. You have no idea about what kind of like RAM requirements or memory requirements people are going to be coming to you with. You're often going to be on memory limited devices as well as compute limited devices. And you're not so interested in throughput. There's likely only one user using the system, but you probably care a bit more about end-to-end latency, or the speed of, especially decoding speed. And you care quite a bit about decoding speed. And this is what the user is going to see flashing across the screen. So these are the sort of things that you care about in like a local deployment. And in a multi-tenant deployment, you don't care so much about portability. There's only a handful of commonly used pieces of hardware in sort of data center deployments. It's going to be up once and run for a long period of time. These are sort of high performance machines. You don't care so much about things like binary size. You can always expand the machines out to get more memory, sort of scale outwards to get more memory. So you don't really care about any of these things. What you probably do care about is throughput. You want this, you're paying a lot of money for these GPUs. You want it to serve as many people as possible, as quickly as possible. So you care about things like throughput and all sorts of performance metrics like time to first token, inter-token latency, things like that. Like you care about sort of the sum of all of these performance metrics. And so everything is geared around this particular this particular meaning of performance. And so let's now discuss some of the sort of common inference engines that you see in each of these categories and how they go about optimizing for these trade-offs. So in the left category, we're going to include things like Llama.cpp, or Llama, which I think is based on Llama.cpp. There's a few others, for example, Mistral.rs, and projects built, for example, on Candle, maintained by Hugging Face. These are inference engines that optimize for these metrics above. They're designed to be portable. And what I mean by portable is they don't rely on hardware-specific or vendor-specific tooling. So for example, Llama.cpp even goes so far as to write its own matmul or matvec, or like its own gem and gemv operations using native C or C++, such that this can now run on any device that can compile C or C++, and that's obviously the vast majority of devices. And so that's good for portability. It's good for portability, but what it does mean is that you can't tap into the sort of speed of light gem and gemv implementations that hardware providers like NVIDIA are able to generate and distribute through their inference engines and their libraries. Sure, I'm certain that there are flags of ways to like link Llama.cpp against Cutlass, so you can use it in these high performance settings. But this challenges the portability and the optimization for binary size and things like that of these libraries, because if I am suddenly using Cutlass libraries or relying on Cutlass libraries for performance, I can no longer run on non-NVIDIA GPUs, I can no longer run on CPUs. I have to ship with my package the Cutlass binaries, which can be really big. And so, or you rely on the target hardware to have them, and that again reduces portability. And so sometimes, tends not to be the sort of default way of using these libraries. All of them do have that ability, but they also come with their sort of custom, will run on anything hardware, and that's good for this portability. These also have like fantastic community efforts in like quantization. The most common quantization format and things like Hugging Face are often these GGUF quantizations that have all sorts of like, code names that are various forms of weight-only quantization, and this reduces the size of the model and makes them particularly good, as I discussed in one of our other videos, makes them particularly good at this decoding speed when you use this weight-only quantization. So these libraries are optimized to make use of these quantization formats that benefit local deployments, but aren't as useful for these big multi-tenant deployments. So moving on to the high throughput data center inference engines, there's tons of examples here. This is where you'll find like SGLang, vLLM, TensorRT-LLM, which you might know by its sort of slightly more packaged name of NIMs, and once again there's sort of many such examples of these. So these aren't attempting to make the same trade-offs as the local inference libraries. They care pretty much solely about performance, and so they'll use vendor-supplied libraries like Cutlass. They'll use optimized binaries, those optimized kernels for attention, like FlashAttention, and they'll use Triton and Cutlass to write optimized implementations of various kernels that appear, like mixture of experts, rope, things like that. All of these increase performance, increase the metrics we care about, but make them less portable, make them a bit harder to run in different places. But the idea is that you spin them up once and they sit there for a long time and generate a lot of tokens. And these are sort of heavily performance-oriented libraries as a result. And so if you care more about sort of the raw performance and making use of expensive GPUs, then you would use one of these. There's sort of a new, maybe emerging class of inference engines that's spearheaded by Dynamo, which actually goes a step beyond these inference engines here. And in fact, Dynamo uses these inference engines, like uses vLLM under the hood, or uses TensorRT-LLM under the hood. And Dynamo it's often sold as a sort of data center scale inference engine. So in Dynamo, it does something called disaggregated prefilling, where the two different halves of an LLM inference job, the prefill and the decode, are done by two different instances of the same model, and the KV cache is transported between them, but we won't go into that now. And it also handles things like scaling of those independent models. It deals with load balancing and makes that load balancing KV cache aware and load aware and things like that. And so it's sort of bridging the gap between the raw inference engine, which might be vLLM, and then some of the sort of distributed features that you might expect when deploying vLLM on Kubernetes, but it's sort of all wrapped under the guise or under the framework of a single inference engine that sort of cares about that. And both vLLM and SGLang work on their own sort of distributed, disaggregated prefilling setup. And there's other alternatives that are just slightly different, but like I think it's called AI Bricks, for example. There's a few that are coming out now, but this is sort of expanding the scope of what an inference engine does into sort of the more distributed world. And so this would be useful if you had a lot of GPUs, you wanted sort of one model running at the highest possible throughput, utilizing hundreds or thousands of GPUs at the same time to back a single API. That would be the use case for something like Dynamo over vLLM or similar. So in this shorter video, we've looked at the two different classes of inference engines, local inference engines and multi-tenant inference engines, and looked at the kind of trade-offs they're looking to make, then gave some examples of those engines. So next time you see a new engine project, figure out which of these two camps it's in, and then decide if that's useful for your own projects.